going. So welcome, good afternoon, everyone, and welcome to today's webinar hosted by RAINA and RDH. RAINA, the Rainscreen Association in North America. Just to briefly touch on who we are. My name is Marcus Jablonka. I work with Darken Systems. We're one of the founding members of RAINA. And RAINA stands for an organization with the mission of working together with our membership, the industry, and trade to be recognized, the recognized authority on Rainscreen wall assemblies in North America. Our vision is to be the recognized Rainscreen authority, supporting performance-driven Rainscreen assemblies that contribute to more durable, resilient, healthy, energy-efficient, and safe buildings. Just to touch on some of our core values at RAINA, we're all about integration of expertise, bringing people together, aiming to support sustainable, long-lasting building enclosures, to generate, together with the industry, building science-based performance criteria, and to do all that while also building aesthetically pleasing buildings and facades. So as members of RAINA, the benefits are to have the ability to influence the industry, to stay informed, to continue in one's own professional development, and to have opportunities to network and gain recognition amongst industry peers. So in case you wish to get caught up on previous seminars, because today's webinar is part of a series of 8. It's number 7 actually in the series. If you missed some of the previous ones and would like to catch up, you can scan this QR code here on the right-hand side, or you can reach out to RAINA and we'll make sure you get a link somehow to watch some of the previous webinars in video form. So today we're going to continue in the series deep dive into Rainscreens with our number 7, which is called The First Line of Defense. And it will be presented by Dr. John Straub. For those, perhaps there are some that have not met Dr. Straub yet or don't know him yet. Let me give you a brief introduction. John is a principal at RDH Building Science. He's also a professor at the Civil Engineering Department and at the School of Architecture at the University of Waterloo here in Canada. He's a structural engineer. He's a researcher. I would say a blend of both pragmatic and ivory tower. He's a forensic expert. He's an author. He often gets engaged as expert witness. And I think to me personally, at least first and foremost, he's an extraordinary mentor to peers in the industry, helping everyone to understand building science a bit better. So we're very excited to have him present today's webinar titled The First Line of Defense as part of the Deep Dive into Rainscreen series. John, with that, we're excited to have you. I'll pass it on to you.
Thank you, Marcus, and kind words. Thank you very much. Yes, as Marcus has said, this is like session number 7. So we've had a bunch of, I think, fundamental discussions in the past 6 sessions. And today we're going to actually talk about, basically, I could have titled this cladding, but we'll get into why we're not thinking of it just as cladding throughout the presentation. So I always start these presentations with a reminder. RAINA has put a fair bit of work into identifying some definitions for words that are commonly used and misused in the building industry. And one of those things was always Rainscreen, and different people have different meanings for them. And so here's the definition that a committee came up with, which I think is, I know it seems kind of academic, ivory tower, but actually it does help us in practice, as we'll find out. So a Rainscreen is an assembly applied to an exterior wall which consists of, at a minimum, an outer layer, an inner layer, and a cavity between them sufficient for the passive removal of liquid water and water vapor. So what that looks like as a concept sketch, and we'll add some more meat to this, is that outer layer, we would generally be calling that cladding. Sometimes, again, words are not always that well defined, but the skin can include the whole enclosure. But really, this is just the outer layer of the entire enclosure. Then there's a gap or an airspace or a cavity. Then we have the inner layer, which we would generally call a water resistive barrier, or WRB. In Canada, WRB is not actually in our codes and standards. We use the term sheathing membrane. But in practice, on job sites and design offices everywhere, people all use the term WRB, and it's a water resistive barrier, not weather. And then, of course, you need flashings so that the water that does drain in that space can be directed to the outside through weep holes or other types of openings. Now, that's your very simple, very bare bones. Today, most of our wall systems have more components that aren't required to be a Rainscreen, but are frankly required to be a successful wall system. And things like insulation, particularly exterior insulation, is common now, but insulation almost always. We have an air barrier that's generally even now a code requirement in most places. And if you have continuous insulation, then we need some sort of a system to attach the cladding back. And so the cladding connections and cladding attachments were covered in a previous session, but they are quite an emerging area of building products. And that's kind of some of the things we need to change to bring our buildings up to the modern expectations of performance. Okay, so let's, again, looking at that sort of set of requirements, we had a session number 1 was an introduction. Session number 2 described the history of how Rainscreens came to be understood and researched and how they were developed in codes, standards, and practice. In session number 3, there was a focus on how liquid water was removed from cavities. A whole session on that, quite important. Session number 4 was how we used cavities and airflow through them to remove a water vapor, passively remove water vapor. By passively mean not driven by a fan, but driven by the wind or sun or something. And then number 5, it's a very important component of our wall systems, is the water resistive barrier. This is also the second line of defense in the Canadian code language. That is an explicit term used to say you have to have a second line of defense. And this session is going to therefore talk about the outer layer. That outer layer, in some ways, we often dismiss it, I guess, or we don't put weight on it when we're describing Rainscreens, because there's a lot of other opportunities to learn about what cladding you can use and how to use it, and they're very industry specific. But this session, I want to talk about cladding in sort of how it ties together with these other parts of a Rainscreen and put those two pieces together. So the outer layer, we would call it probably cladding today in many different ways. It is the exterior finish of our building enclosure, or it's what the building looks like. In many cases, people who aren't specialists in the building industry would be pointing at a building and saying, what we're seeing here on the right side, oh, that's a metal building. Or they might say, if it were brick, they'd say that's a brick building. So that exterior look obviously has a pretty big impact on how people experience the building, which is why we see in design a lot of effort spent on what that cladding is and does and what it looks like. So, but it's more than just the look and the feel of the building, of course. From a technical Rainscreen point of view, its biggest job is that it sheds rainwater that is incident on the surface. It is the first line of defense. The water that strikes the building is going to strike the cladding first. And when we have a cladding that's designed to shed the water off a lot, then we don't have to worry as much about these other components. Another thing it does is it blocks the view of underlying layers. And both these kind of core Rainscreen functions are being experimented with in modern construction. We have claddings that do little or no screening of rainwater. So that's what I want to talk a bit about today. And we also have claddings that sometimes barely block the view of the underlying materials. So we want to talk about how that affects the design, because both of those things matter quite a bit to how you would design a Rainscreen building. Now, you've probably heard before, maybe even from me, that almost any cladding material can be used to as a Rainscreen cladding, but it's much more complicated than that. So for example, this is a picture that Graham Finch took or provided me, anyways, and that's somebody using LPs nailed together in an overlapping shingle fashion to provide a Rainscreen. And actually, for a bunch of applications, this would be okay. But I want to also come back and look at this and say, so what doesn't this do well enough, and why couldn't we use it in some applications? But we clearly can in some. Here's another one, a much more, let's say, a green Rainscreen cladding. So it actually performs a lot of the functions. One of the drawbacks of this particular approach is that when the season comes to an end, so does your Rainscreen cladding. But that doesn't mean that, it's not doing something right now. So while I said looking good and shedding rainwater, now let's talk a little bit more about the technical aspects of the cladding's requirement, because I can spend hours talking about all the forms of fiber cement, high pressure laminate, terracotta, polycarbonate, porcelain, masonry, et cetera, et cetera. But really, most of the time, designers have an idea of what they want it to look like, but then we have to say, and can it technically meet the requirements? So as an example, can it resist or survive or tolerate UV exposure? Ultraviolet exposure is obviously a critical variable of the weather, which, by the way, to answer Michael Scantlin's comment in the chat, is that's why it is not a weather barrier. It's not even a moisture barrier. It has to be a water resistive barrier, because it actually can't resist things like temperature. That's why we have insulation on our walls. And cladding is there to resist UV. Now, we're going to find out that for special cases, you might want to have a water resistive barrier that can also resist ultraviolet radiation. That's a special category we're going to briefly look at. Another thing you might have is that you might have a water resistive barrier that's also supposed to be a vapor barrier. That's a special category. Vapor is a form of moisture that isn't like water is a form of moisture, vapor is a form of moisture. The reason we have a word WRB is to distinguish between vapor barriers and water barriers, because they're different forms of moisture. So that's why that language and these definitions are actually quite important and cause improper product substitutions on job sites and mistakes being made in specification in the first place. Now, another thing, once we've got our UV resistance managed or fading, then we have to think about rain damage, or let's call it moisture damage, really, moisture of all sorts. And it often can result in staining. Of course, in the worst case, it can cause corrosion or decay, or dissolution is the term for dissolving components. Sometimes when we dissolve components, they leach out of the assembly. These are things that, of course, we don't want our cladding to do. And we have to make sure that whatever cladding we're choosing is not going to do these things. The image on the right-hand side is just a pretty standard image that I've chosen, but it has different claddings in it. And we see a metal, we see a fiber cement, and we see a masonry or mineral-based product. Those three different categories, mineral, metal, and wood, let's call it fiber cement, is more of a wood or polymer product, have very different responses to the weather conditions. So metal is unaffected by temperature and freeze thaw. However, it will corrode if you don't protect it from rainwater or don't allow fast drying. The masonry will be very resistant. It doesn't corrode at all, and it doesn't care if it gets really hot. However, freeze thaw damage, leaching, and salt can all attack mineral-based materials like that. And so each of the types of cladding systems have their strengths and weaknesses, and it's our job to select those cladding materials and the cladding product to be appropriate for the exposure. And I don't just mean the exposure, meaning what site you're on, whether you're in Cape Breton where you get lots of rain and lots of freezing, but also what about if you're in Phoenix, Arizona, where you get a tremendous amount of ultraviolet radiation? What about if you're on the north side versus the south side? Things like this, understanding. On the impact damage and the freeze thaw damage requirements, the base of the picture I'm showing you, the building that's shown in this picture, is a masonry. And it is one of the reasons it's chosen in a school application like this is to be highly impact damage resistant. So they tell me that, students in, say, grades 6 to 10 can be rather rambunctious and run things into walls, whether that's bicycles or each other. But it is a wise designer who recognizes that you need to have a scratch resistant, impact resistance, bang resistant, whatever you want to call it, cladding at certain parts of a building. Often that part of the building is at the bottom of the building. And also different types of buildings have much higher requirements than others. So that really limits that, for example, that vinyl record cladding system. If we installed that along this wall at the entrance to a school, it's almost certain that those vinyl records would be ripped off the wall in chunks and pieces within weeks of that school opening. So so it maybe meets the role of being rain shedding and even looking good to some people, but it wouldn't meet a lot of these other sort of requirements. So this gives rise to less quantifiable issues such as maintenance. How much maintenance is required? Do you have to wash it every year like you do, say, a glass window? Or do you have to, how do you remove graffiti when it ends up? This is an important requirement of many cladding systems, is that the owner, through experience, will say, I need to have something that is graffiti resistant and or I can remove it easily. So it's not an uncommon requirement. How do you repair and replace a damaged or broken or whatever cladding? There's many cladding systems that you can assemble in one way, but if you have to remove any arbitrary panel, some systems are easy to remove an individual panel, and others you have to undo a whole bunch of the other pieces of the cladding before you put the replacement piece in. And then we also have claddings that it's very hard to match. So if I get a new piece of cladding a year after the building's built, how hard will it be to get something that matches and so it doesn't stand out? Now, this can be addressed in design by making sure that the panels are not all identical to begin with, so that when you have to make a change in 5 or 10 years because of somebody ran their pickup truck into it, you don't have an aesthetic eyesore. Another practical and highly quantifiable requirement is often weight. Now, we rarely get a weight restriction in design, in my experience, unless we're doing retrofit. Sometimes in retrofit, the backup wall can't bear much weight. And so we're given pretty strict limits on whatever system you choose has to weigh less than X. X could be 3 pounds a square foot or something like that, which really limits your choices. But in new construction, the normal approach is to say, I want a lightweight, air quotes around that, cladding. And so we really do want to understand, well, are you meaning 7 pounds a square foot, or do you mean 4? We'll talk a bit about that. And then there is required fire properties. Now, there's a can of worms. I am not a fire consultant, but I have to know that we are seeing a lot more questions being asked about what do we do with fire requirements? Does this meet the fire code? Does that? And so this is an area of lots of growing questions and interest, which probably needs some additional sessions. And Raina, I'm certain will be dealing with this in the future. But when I put down the acronym WUI, I'm talking about the wildland urban interface. This is an area that is defined in an increasing number of parts of North America, which enhances the fire resistance requirements of the exterior of the building, under the assumption that it is not your neighbor's burning house that's going to cause you damage. It's not your burning kitchen stove that's going to burn through the walls from the inside. It is the outside wildland, whether it's grass or trees or shrubs, is going to be the fire risk. And that may limit what kind of claddings you can / should use. So those are some of the many and varied requirements. I haven't even really talked about things that people often talk about, which is price, availability, trade installation. These are the things that are, I would say, are non-technical, but are clearly really important in practical design and the selection of cladding systems. So this is a scale on the bottom from RDH. I've added some letters, some other concepts to this, but just to put it in context, we typically consider lightweight claddings that are well under 5 pounds. And that means fiber cement sidings, high pressure laminates, EIFS, most metal panels. A few plate metals can exceed this, but that's pretty exceptional to have it that thick. You can see vinyl sidings at the very bottom of this. It's one of the lightest weight claddings. Well, that's partly it's a part of its charm, I suppose. And then as we move away from fiber cement, we can get into some thin reinforced concrete panels. By the time we're at stucco, a proper stucco, that's a 3/4 inch, let's say, or 20 millimeters, then we're dealing with already 10 pounds a square foot. By the time we get to thin stone veneers, we're in the 10 to 15 pounds a square foot. And those adhered veneers is what I'm describing, where you have cut or stone or manufactured stone that you adhere in a bed of a mortar-like adhesive. They're actually limited by their trade association and the U.S. code to 15 pounds a square foot. So that's sort of the end of where most lightweight claddings could ever be thought of. Then we start moving into masonry at all the way up to 6 or 8 inches of precast concrete. By the time you're at 8 inches of precast concrete, that's how you get to 100 pounds a square foot. Now, that's a vast range. And the reason it matters to Rainscreen design has nothing to do with the mass. The reason it affects Rainscreen design is that the cladding attachments that penetrate insulation, that changes. And so this may influence ventilation, drainage, the quality of the water resistive barrier, all of those things. So that's why mass will matter. In the overall wall design, the mass of the cladding is really important. So I mentioned also fading. This is a personal, close to my heart example. This is the University of Waterloo School of Architecture in Cambridge, Ontario. And when the building was newly constructed, the building looked like it did on the left. The aluminum was shiny and the fiber cement was a dark charcoal color. And then after 10 or 11 years, I think this photo is actually 11 years, the color of that dark color had completely faded away. So, and this is particularly a challenge with dark colored of all types, but normally if you're using mineral-based pigments, it will survive this. But it's, again, I'm just pointing out it's a question you need to make it work. Yeah, as somebody said, hey, it still looks good after 10 years. It actually does. It's just surprising how different the color is, and it's unclear whether the architect expected it. So anyway, just keep that in mind. And when it's a very light colored cladding, we have the opposite problem of soiling, often biological soiling, like algae, moss, and mold, mildew growing on the surface. Not because the material of cladding supports that, but because dust from the air lands on the surface, and then you get growth on that. So, as I mentioned, in the Canadian Building Code, the National Building Code of Canada, it says cladding is defined as the first line of defense. And that's what we titled this seminar. But this means there's no need to seal the joints in a watertight manner, whatever that means. By definition, a Rainscreen it allows water to go through the cladding because it has an entire system that accumulates that water and directs it harmlessly back outside. So the reason I highlight this, though, is that when you're doing drawings and more importantly, sites reviews and inspections, there's no reason for people to do an excellent and perfect job of using sealant on the Rainscreen joints or the joint between the window and the Rainscreen, because by design, there must be drainage behind that. And a small crack or opening should not worry you. If it does, then you need to either not make it a Rainscreen, or you need to do a better job of the WRB and the cavity and the flashings and the weep holes. Now, that said, the opposite is meaning no sealant, completely open joints, is a challenge because there's a limit to how much water most systems can safely handle. We're going to talk a bit about that. But open jointed cladding systems clearly allow a lot more water in. And that might change how you do your WRB, your flashings, your inspections, etc. Which gives rise to the concept of a baffled joint, which is a joint that is unabashedly not waterproof or watertight, but also does try pretty hard to keep water out of that drainage space and away from the WRB. One of the rules of rain penetration control and management is that if it doesn't get wet, it won't leak. And so when we're designing this first line of defense, if we do a good job, well, then our second line of defense, the water resistive barrier, actually doesn't get challenged as much. Then our flashing doesn't see as much water. And that means that our chances of success go up dramatically. So in that vein is to think about this sort of in a hierarchy. Cladding is shedding rainwater. The cavity, or rather the two sides of the cavity, provide drainage. And the cavity provides ventilation to dry out the water droplets that are there. And the water resistive barrier, defined in the code as the last line of defense, is to deal with the remaining water that gets to that surface. The reason we don't use roof membranes as WRBs in our Rainscreen wall systems is that when walls are installed vertically and when you have a cladding over them, the amount of water that membrane sees is vastly less than it would be on a roof membrane. And so we can choose much different materials better suited to that task. And that's how we have success with things like house wraps and relatively thin peel and stick membranes. Now, when we get to open joint claddings, I'm just showing you, these are both masonry veneers that are installed over a cavity and a WRB. And the one on the left is about 3/8 of an inch. It's actually, I think it's 10 millimeters, was the specification. And the one on the right is as little as 1/8 of an inch, which is a 3 millimeter spec. And that's actually, the 3 millimeter is hard to do because you need to have everything plumb and level to make sure that the stones have to be cut really carefully to allow that small of a joint. But it obviously is going to let less direct driving rainwater in, but not as little as you'd think. The joint on the left will let a fair bit of direct rainwater in, and therefore you have to plan your design accordingly. So about 50 to 60 years ago, there was a lot of research into joints and joint design. And when it came to these joint design openings, they were looking at how pressure would equalize across the cladding, a topic for our next session, and also how much water would either be directly dragged into the opening or be blown in by airflow. And so one really cool report from 1974 from the Building Research Establishment in the United Kingdom is this Herbert report, where they built a test building on the edge of a cliff in one of the rainier and windier parts of the UK. And they actually physically measured how much water came through joints with different amounts of wind speed, rainfall, and blah, blah, blah. Okay, so this one is showing, there's a lot of data here. You can look at this when you look at the slides later in more detail. But really, in short, it said that when the joint got too small, it increased the rate of water entry. And by what I mean by a joint, the joint width is in the bottom axis. But if you had the joint, when it was a ventilated joint, if the cavity was large, it didn't matter as much. But if you look at the bottom, the 13 millimeter wide cavity, and you look at the open joint, a lot of water was coming in with joints that were 2 and 6 millimeters, which is something like less than a 16th of an inch up to a 1/4 inch. And then as the joint gets larger, the amount of water that entered would go down. And when we got to a joint larger than 13 millimeters, or 1/2 inch, the water entry goes up. Okay, why is this? Well, somebody asked about capillary action. Well, when you get a small joint, 1/8 of an inch, water running down the facade will be kind of wicked into that joint because of surface tension, which when it gets into the joint is called capillary suction. But the water won't leave the joint. So the same force that drags the water into that crack is resisting it leaving that crack. However, what happens is with wind gusts that have short spikes in pressure, the water in that joint, if it's small, can then be pushed in. If the joint is really small, like less than they tested here, then it'll hold the water like with so much surface force, like you can't blow water out of a brick. Capillary suction holds the water in the brick. But in the joint sizes that we practically talk about, 1/8 of an inch or so, water is just held in there a little bit. As you go to a 1/4 inch, water isn't really bridging joints in normal rainstorms. It rarely occurs. And by the time you get to from a 1/4 inch, you get up to something like even 5/16 of an inch, 7/6 of an inch, then it absolutely, the water will drip across the joint rather than be held in the joint. And that limits the amount of water that goes in. As you get to inch-wide joints, now we end up with literally sometimes rain droplets coming right in. Now, these tests here were done intelligently with cladding that was only a 1/4 inch thick, that's 6 millimeters, and with a cladding that was 64 millimeters or 2.5 inches thick. And the depth of that cladding, and therefore the depth of the joint, also matters. You know, if you have a very deep joint, then direct rainwater just doesn't make it in. And that's these field tests, not lab tests, which are always a bit suspect. These in the field tests actually showed all of this. I'm just going to show you a little bit in practice what some of this stuff looks like. So you see here, that is a baffled joint on the left. And what's interesting about it is that this is a formed U-shaped metal or a hatch section, but it's been perforated. And so it actually allows all kinds of air to enter behind these cladding panels. But at the same time, it keeps out insects. It keeps out the annoying finger of inquisitive engineering professors. And it also aesthetically finishes the building and resists UV radiation. So all of that's working well. And it's not a common detail, but I think it's really a very good one. On the right-hand side, we're seeing a more typical installation of a thin, I believe in this case, it's something like 3/8 inch thick fiber cement compressed panel. All the joints are backed with a sheet of black painted metal. And so the joint isn't fully open, but it has many of the benefits of an open joint, which are we have no sealant that we have to maintain. It makes a very clear aesthetic distinction between panels. What it doesn't do is it doesn't, like open joints, allow a lot of air to flow into that space, and that can help with your ventilation. This case, it's under construction, the building, but in this case, the air will be brought in at the bottom to provide ventilation. And so they're going to have pretty good ventilation space here, but it comes through an open slot at the bottom over top of a flashing detail. And we actually can do we can mix and match. Vertical joints are quite important in buildings, in claddings, as much as horizontal joints. So this is an interesting commercially available product that shows on the right-hand side, you can see the 3 dimensions. It is using lapped joints on the horizontal, which means that they're not open joints. They're completely protected against insects and fingers and driving rain and sun. But as you can see on a photograph on the left, they read quite strongly as a joint. And the vertical joints are where these panels come to an end. They just would normally butt together and not necessarily what's desired. And here they're holding them back, making a joint, and also protecting that joint by using a hat section in the reverse hat section. So any rainwater that comes in, sun that comes in, first has to get past that. And so these are baffled joints which dramatically reduce the amount of water that can get into these spaces. And frankly, they work probably as well as any sealed joint will work, sealed with caulking joint, given the propensity for sealant to have occasional cracks, openings, and failures. So here's another example. This is from our friends at Morrison Hershfield, now Stantec. Design considerations for open joint Rainscreen cladding. And it's just showing in Europe, the image on the left is a more common product or system. They're more likely to use wood furring on commercial buildings, and EPDM gaskets, as shown, are a way of actually getting a fairly well sealed joint. Some might think it's even, we don't have to go that far, but it certainly works as a baffled joint. And then if we look here on the right, a typical horizontal joint of a metal panel that's bent and turned up. And so that's what I think most of us are used to seeing, is that joint is not open directly to rain. However, it can be very open for air because the upper lap doesn't have to go over the lower lap, and it doesn't contact. In fact, often it doesn't. In details like this, you can leave it quite open. And so you can get a tremendous amount of airflow through, but absolutely block sunshine and fingers and rain. So that, just sort of thinking through summary-wise, if we think about lap siding, it is actually doesn't allow much water through at all. Where water gets through lap siding designs is at the butt joints, because these panels all have limited lengths and they run into trim around windows and doors and balconies, and that's where a lot of the water will come through. But actually those laps, pretty darn effective. And so the amount of water that hits a WRB is pretty small. many of you will recognize that that describes a lot of single-family houses built in North America, is that we use lap siding over not a high-quality WRB when compared to, say, a peel and stick membrane that might be 40 mils thick. Now, if I have now a cladding that has unsealed or unlapped joints, and you might have quarter-inch gaps between them, we will get a fair bit more water coming through. Now, that water will likely run down the back side of the cladding, but more of it is likely to cross the cavity and get in contact with the WRB. So with a cladding like this, we'd start to think that we need maybe a better quality of installation, better materials, better lapping details, etc. But really the big change comes when we move towards the open jointed and perforated claddings that allow for routine and direct access of water into that space. And then this is where we definitely are thinking we need a better quality WRB. And I also point out it's not just buying better materials. You might very much want to buy better quality control, more inspections, more people there making sure that the details are being done the way they're designed, because that reduces risk in the same manner as choosing a more water resistive WRB. So if adding insulation to the outside actually helps a fair bit as well, because rainwater that now gets through, it doesn't actually directly contact the WRB. First, it has to contact the insulation. And so here we're looking at a couple of details showing ranges of water entry. By the time we look at an open joint like this, we start asking the question, do we have maybe so much water that I need to add an additional water shedding surface? So if the cladding is doing a very minimal or zero job of water shedding, then we can always add a simple and less expensive water shedding layer on the outside of the insulation. In residential, this might be something like you use building paper. You're still using a good quality WRB combined with an air barrier at the sheathing level, but you're now adding a layer that enhances the number of drainage surfaces and their quality because you allow the water in through the cladding. And then finally, when we have highly perforated claddings, then you start thinking about having pretty good quality exterior or high exposure. Let's say you're in Cape Breton, then you have high exposure to rainwater driven by wind, and that's important as well. So these are the kinds of claddings I'm talking about when we say they're highly perforated or highly open. You can see, I mean, on the left in the middle there, those are they really even claddings? In terms of rainwater, they do make a difference. Don't kid yourself. I mean, we've measured some of this stuff, not in real rainstorms, but with spray tests. And even claddings like the building, the New York University Catholic Center there in the middle, there's a lot of water that is shed off that front face. So that is pretty effective. However, you can see that there's still a lot of water going to make it to the backup. And in fact, if you look more closely at that middle drawing, you can see at the windows, they didn't even bother with a return. And there's actually a 4-inch or 5-inch cavity, I forget, something like that. And their WRB is something like a 20 gauge sheet of aluminum that are large sheets of aluminum that are UV resistant and waterproof. It's basically a curtain wall where someone added a screen to the outside. So we get a lot of questions these days in wood cladding, where the intention is we know the benefits of ventilating behind wood siding. It really enhances durability, limits cupping and bowing, enhances paint life if you paint. But we start to have questions about, but what happens if you have thick enough cladding and water can sit on the top edges? So in some cases, people are actually beveling the top of the wood, although I warn you, it takes a fair amount of bevel to make water run off of wood. So what we do in a lot of these open jointed systems to protect or enhance the performance is to use a UV resistant membrane. It is, as I said earlier, a WRB is not weather resistive. Many of these products will have as little as a 30-day warranty to being exposed to sun before you have to cover them up. And this has become a bit of an issue in some jobs where, especially commercial buildings, how many people can actually have a construction schedule where you put up a WRB and then protect it from UV exposure within 30 days. So that has led to some manufacturers extending warranties, but more importantly, some manufacturers doing something about it and producing UV resistant or giving you reasonable lifespans. The extreme example I can think of is that in parts of Texas, like I know around Austin, areas in Houston, where the preferred WRB is an aluminum foil-faced piece of bitumen, because the aluminum has an indefinite exposure that's allowed to their intense sun. So keep the WRB and its UV resistance in mind, not just for when you have open jointed cladding, but thinking about it in general. So this is an example of both using a membrane that is UV resistant, as well as acting as a secondary drainage layer. So now this is the outer water shedding layer that basically takes over most of the water shedding function that cladding with closed joints would do. So cladding with closed joints might do 99% water shedding. That's not an exaggeration. Cladding with open joints might only do 90% water shedding. So then you use a membrane like this, all you're asking for it to do is do 99% of what it sees. And that means that the primary air and water barrier, usually a fully adhered membrane behind the insulation, is seeing a lot less water and can easily handle. So that leads to this open joints. Beware of thick claddings, because as I mentioned, if you have a thick cladding and you have a flat top, water can sit there. And in many materials, this can cause problems. Stone and wood being the primary ones. I was going to say this slide here is to remind you of, we talked about cavities and how they affect fire. But now I also want to say, but remember, all these drawings that we showed in the previous session are assuming we have a non-combustible cladding. When you have combustible cladding, there's a big change in fire performance. And so this needs to be considered in cladding choice, depending on the type of building you're dealing with. We also have to think about these secondary water layers, not just behind open joint claddings, but the moment I take my cladding and I turn it on the side, I end up changing how much water goes through the cladding. So this is an example that I've given in other presentations, but more importantly, just take a look. It's a 5 to 15 degree slope on some of these walls. The profile of this quality material, it's a durable, color fast material, but the design of it was to use a horizontal lap to keep most of the water out, to be water shedding. But notice the jointing here between the butt joints, which occur every 12 feet, will allow water that's running along that little trough that's been formed to run into the cavity. And our tests on the site by just spraying water on the cladding showed that, no exaggeration, 100% of the water sprayed on slope portions of this cladding went past the cladding and then entered onto the remainder of the building. And so the remainder of the building looked like this. And so that membrane, which is obviously a pretty high performance membrane, had to see all the way 100% of the rainwater that was on that surface. I wouldn't have been able to tell this story if they didn't also install the horizontal Z-girts or Z-girts there, which also made sure that the water didn't run away. And that caused some additional challenges. Now, let's get a bit more practical. if you have a sloped roof, sloped wall, I don't know what the difference is between a roof and a wall. As soon as you slope it, it's a roof. This is an open jointed cladding system on a roof, and it works. And it works because they used a multi-layer approach. They knew they couldn't rely on the water shedding of the exterior cladding. So they used a UV resistant water barrier right behind that open joint to do the water shedding function. And then the primary air water barrier was put on the deck like it normally would. So this is making us think a little different about just single layers of WRB and cladding as you can use whatever you like. No, you have to connect these ideas together. It's exposure, it's how open the joints are. Do you have deep windowsills like I'm showing you here, which collect water? This is a place where you'd probably be using 2 layers, a water shedding layer underneath the cladding, and then the fully adhered air water barrier underneath it. And then finally, to end off here, I also will throw you another little challenge to think about is don't just think of the cladding for the whole building. A major challenge is how we handle that transition to grade, how we deal with the impact loads, the de-icing salts, the landscaping crew who seem to want to attack us. Now, on the right-hand side, we have a stone that can't handle de-icing salts and freeze thaw. And on the left-hand side, we have a product that can, a higher density granite. How we deal with these bottoms can really affect the aesthetics of our building. You'll notice the picture on the bottom left is cement board faced extruded polystyrene, which doesn't come in curved segments. So when the building has a curve on it, like this one does, the trade's response is to say, I give up. And that's how we ended up with that. So that's just a wrap up of saying there's a lot of functions that a cladding has to perform and a lot of constraints. Make sure we don't lose important ones. But when it comes to the rain screen and rain penetration side and a little bit on ventilation, the joint design is key. And you need to adjust both what you're doing in your cavity, your kinds of WRBs, or you're using a secondary water shedding layer. Think about quality control as a way of managing all of those challenges that come with the wide range of systems that we have available to us. So we only have a few minutes for questions, I think, but I wanted to remind everybody here that there is this annual symposium for RAINA combined this year with ABA, the Air Barrier Association, and it's coming up next week. So I don't know if Marcus, if you've been paying attention to questions and comments or what's going on.
We have a number of them, so we'll jump right into that. One is from Rob Klein. Do you categorize eaves as rain screen?
Oh, great question. It depends. How do you like that for a consultant's answer? Well, it would be a rain screen if it has that drainage space and a drain opening at the bottom. The real question here is whether or not it allows for passive removal of water vapor, because we usually do not want to ventilate an eaves, meaning allow through flow of air, because we'll lose the R value, a lot of the R value of that insulation on the outside. So eaves are widely deployed as effective drained systems, and they might not need to be a rain screen, meaning they might not need ventilation because they don't absorb a lot of water or pass a lot of water. So I think by today's definitions, they're not usually a rain screen, but that doesn't mean they're not highly effective.
Thank you. Another question here is, what is most commonly used as the UV resistant water shedding layer in behind open joint cladding systems? Are they just using tar paper, even on larger commercial projects? Any concerns with trapping 0.5% of water or moisture now between the WB and this layer, which has no airspace now?
That's a long question, but it's a good one.
Long question.
Okay. So first of all, tar paper has marginal durability if you have any kind of larger openings. It's also susceptible to wind damage. So from a commercial, more high exposure, I would never recommend that. But there are a couple of products, one of them made by a company called Dorkin, actually, out of Beamsville, Ontario, called Facade S, which is a membrane that is UV resistant, both fully adhered and loose. So you can buy these products that are bespoke for this application. On the point about, am I worried about 0.5% or 1% of water getting behind that layer? Absolutely not. Water doesn't need a large gap to drain. It'll easily drain behind that loose applied membrane, easily, without any hesitation at all. It's just that you can't seal that layer up as a WRB normally would. You are just installing it in a lapped way. Loose, lapped, water that gets in can drain out at the laps, and the actual real water and air barrier is back here behind the insulation. That's usually self-adhesive and taped and held on firmly.
Very good. Another question here. What is the extent of concern related to penetrations through the WRB? Screws, fasteners, etc., with an otherwise effective wall system design?
I'd say, well, as a high-level comment, holes through your WRB are bad because we've discovered that most leaks occur at holes. Okay, but the reason that that question depends so much is that we know that you can put nails and fasteners through WRBs by the thousand and not have problems. That's how we have built most buildings and houses for decades. The reason that we have to ask that question more often today is that, well, again, it depends on if you are, the moment you are off vertical, you can't rely on gravity driving the water past that hole. And also, if you have a lot of water on the surface, then those holes are a problem. And so this goes back actually to the thesis of this presentation. If you have letting a lot of water in through that cladding, I start to worry about cladding attachment clips and nails and screws, etc. And that's when we need to use gasketing, sealants, etc. And so it really is, it depends. It's a judgment on how much water do you think is going to get to that location. And if the answer is a fair bit more than normal, that's when you start worrying about nail holes and screws. But we know from practice, for 50 years of putting nails through house wraps, building papers, and peel and sticks, that leaks don't occur there in normal exposure with normal amounts of water. So yeah, it's about as far as I mean, there's a whole seminar I guess one could do on this, but that's how I can summarize that question.
Maybe number 9 in the series. There's another interesting one question that is waterproofing products keep being bought and sold by different companies. How do we keep track on whether those products still maintain the same raw material formulation and perform the same and have no compatibility issues with other products?
Well, frankly, I think that's a great question. It's one we ask ourselves probably every week at RDH. And if you find out the answer to how to do that, please share it because we're all looking for that too. I don't know.
Good question. How to address air leakage value of performed metal panel wall rain screen? Sorry, of formed metal panel wall rain screen.
Well, I guess it doesn't matter whether it's a formed metal or a brick rain screen. The air permeance, the air tightness test is being done on the air barrier, which is independent of that. So I'm not quite sure if that's what you mean right now.
Not sure either. Maybe the person that asked the question will have to follow up. Any tips on using insulated metal panels without backup wall?
Be very, very careful. So anyway, we actually have to wrap up today at around 2:00. But seriously, those insulated metal panels rely on good dimensional control at the joints. And if you can ensure that, make sure that you have sealed joints. I would do some additional testing to make sure that happens. Then you don't need a backup wall. the reason we've moved to backup walls has been more so that, well, that's probably not worth the hassle, and it's easier to run services and hang drywall if I just put up a stud wall and then use the insulated metal panel as my primary exterior. So again, a little bit complicated, but you do need to, you can't assume it's easy, that you get that tightness. All right, Marcus.
We'll have to wrap it up. Thank you very much, John.